Let's solve a classic thermal equilibrium problem involving heat transfer between hot copper and cold water. We have a hot copper sphere at 200 degrees Celsius being dropped into cold water at 20 degrees Celsius. Let's start by identifying all the given information in this problem. The copper sphere has a mass of 0.5 kilograms and starts at 200 degrees Celsius. The water has a mass of 0.8 kilograms and starts at 20 degrees Celsius. Importantly, the system is insulated, meaning no heat escapes to the surroundings. Here's a summary showing the mass and initial temperature for both the copper and water. The key principle we'll use is conservation of energy. The heat lost by the hot copper sphere must equal the heat gained by the cold water. We can write this as Q lost equals Q gained. The heat transfer is calculated using Q equals mass times specific heat times change in temperature. Heat flows out of the copper and into the water until both reach the same final temperature. We need the specific heat capacities for copper and water. The specific heat of copper is 385 joules per kilogram degree Celsius. The specific heat of water is 4,186 joules per kilogram degree Celsius, much higher than copper. We denote copper's specific heat as C copper equals 385, and water's specific heat as seawater equals 4,186. Now let's set up our conservation of energy equation. Mass of copper times specific heat of copper times its temperature change equals mass of water times specific heat of water times its temperature change. The left side represents heat lost by copper as it cools down from 200 degrees. The right side represents heat gained by water as it warms up from 20 degrees. Substituting all our values, we get 0.5 times 385 times 200 minus T final equals 0.8 times 4,186 times T final minus 20. Let's solve this equation step by step to find the final temperature. Simplifying the coefficients, we get 192.5 times 200 minus T final equals 3,348.8 times T final minus 20. Expanding both sides gives us 38,500 minus 192.5 T final equals 3,348.8 T final minus 66,976. Moving all T final terms to the right and constants to the left, we get 38,500 plus 66,976 equals 3,348.8 T final plus 192.5 T final. This simplifies to 105,476 equals 3,541.3 T final. Dividing both sides gives us T final equals 105,476 divided by 3,541.3, which is approximately 29.8 degrees Celsius. Let's verify our answer makes physical sense. The final equilibrium temperature is approximately 29.8 degrees Celsius. This temperature is between our initial temperatures of 20 and 200 degrees, which is correct. Notice it's much closer to 20 degrees than 200 degrees because water has a much higher heat capacity than copper. Here's a temperature scale showing how the final temperature of 29.8 degrees is much closer to the initial water temperature. Let's verify that energy is conserved by calculating both sides. Heat lost by copper equals 0.5 times 385 times 200 minus 29.8. This equals approximately 32,789 joules. Heat gained by water equals 0.8 times 4,186 times 29.8 minus 20. This equals approximately 32,785 joules. These values match within rounding error, confirming our answer is correct. Let's summarize our final answer. The final equilibrium temperature of the system is approximately 29.8 degrees Celsius. The copper sphere cools dramatically, from 200 degrees down to 29.8 degrees. The water warms only slightly from 20 degrees up to 29.8 degrees. Water's high heat capacity explains why it changes temperature much less than the copper, despite absorbing the same amount of heat.